All right. So last Tuesday we talked about beginning looking at vectors and those concepts. We did the addition and subtraction, the basic stuff there. Looked at figuring out the unit vectors. Now this week we're going to look at two different ways where we want to multiply vectors. So we have the dot product and the cross product. We're going to look at dot product. We'll show you how to find it, and then we're going to see how it's actually used to do stuff. So one of the big things that the dot product helps us do is find angles between vectors, so which is very helpful. All right, so the dot product is, as stated on the screen, it's you'll see it basically looks like multiplication. It will always have the dot between it, will not have parentheses. So that's why it's called the dot product, and the cross product actually will have the X between it that you used to use for multiplication. The dot product will come out with a single number. So you'll get a single answer out of it, not a vector. So you're going to multiply the first terms, multiply the second terms, multiply the third terms, and then add them together. In essence, that's how you find the dot product. So it's not a very complicated process to do. So let's look at these, and then we'll start looking at some of the other stuff and how we can actually use it. All right, so let's find the dot product of the first one. So we're just going to take 2 times 3, and then we're 4 times -1. So that should come out to be 2. 6 minus 4. And that's the dot product. So you multiply each of the positions of the terms, and you add them together at the end. Doesn't matter if it's 2, 3, you're going to do the exact same concept. So this one's 3, so we're going to do it 3 times. So -1 times 6 plus 7 times 2 plus 4 times -1/2. So -6, 14, and -2. So I'd scare you, but it's math class. It's already scary enough. So it comes out to be 6. Hello. The last one is just in the IJ and K format. So in this one, we're missing the I. That's fine. You put a 0. So it'd be 1 times 0 plus 2 times 2 plus -3 times -1. So 4, -3. So this equals 1. That's dot product. We're done. It's actually, that is actually all the dot product is. It's just a matter of let's now actually figure out how we're going to use it. So. Oh, it'd be plus 3. You're right. 2 negatives. Do dot product correct, screw up basic multiplication. So it's 7. All right. Oh, I'll finish writing that down. For the 0, not really that one too. All right, just as we looked at properties with the addition and subtraction, properties, the dot product properties are actually really important as well. So two basically no different than you would do with multiplication. You can switch around. It's not going to change anything because we're multiplying and then adding. So order doesn't really matter. This one, if you think about it, it's just like distributing. The A goes to the B, the A goes to the C. I can move the parentheses in any order as long as it's a constant. It doesn't change the process. If I multiply it by 0, it's going to be 0. If you think about it in terms of what we just did a minute ago, that makes sense. If all of them were 0, 0 times everything was going to come up to be 0. The first one actually is the only one that doesn't kind of like make sense within, like, there's a process to it. The dot product of A and A equals the magnitude of A squared. So remember, to find the magnitude, what did we do? Right, so you square each value, add it up, and take the square root. So if I'm going to multiply each one by itself, that's in essence what the magnitude was already doing. So the only difference is, so if you think about it, if I took two vectors, let's do 3, and 3, 2, and 4, it'd be 3 times 3 plus 2 times 2 plus 4 times 4. It'd be the same thing, right? And then we would do the square root of it to find the magnitude. So if I squared that, that's what that is. So if they're the same, that's going to come. That right there is going to come in really big in a minute when we're actually going to look at how we're going to actually use it. So that's just the only one that just didn't, like, the way it looks, it just doesn't look like it's something like, okay, why is this true? The rest of them all match up with stuff we already know. That one really doesn't. But that's why. All right. So let's use this. Okay. We looked at how to add, subtract, the vectors and how they come up with it and use it. One of the big things that we're always going to really need to know and be able to find is angle between vectors. Okay. I need to find the angle between two different things. So if I'm looking for that angle, and I know those sides, how would I find that angle? What's the, there's a couple laws that we used back in trig. Huh? Nope. That only works when it's a right angle. We don't know what this one is. So what were the two laws that we can use if we didn't know they were right angles? Law of sines and law of cosines. Law of sines, I need a pair. So to do the law of sines, I would need A and A, like the sine of A, or the angle A and then the side A, or whatnot. Law of cosines, I don't need the pair. So in this case, we would need to do the law of cosines. So the law of cosines, basically, actually, I'll use C. That was the law of cosines. Okay. So let's use this to find the angle. So we've got our law of cosines broken down. So if we find our pieces for this, this is, so that right there is the AB. So it's the magnitude of that side there. This would be the magnitude of OA. And that'd be that of OB. minus 2 times OA plus OB, not plus, cosine of theta. So let's change these now into what they are with the vectors. So AB is that vector right there. So that's the magnitude of A minus B squared. That is A squared. That's B squared. Minus 2 times A, B, and then cosine theta. All right. Everybody with me so far? It's the line, the length, the segment. It doesn't make a difference. You could have gone directly from here to here. You could have gone directly from there to there. It didn't matter. That was just the way the book did it, and I'm like, it's fine. All right. Let's work on. Let's just look at this side for a second. So we just did a rule that said the dot product of A and A is that, right? So A minus B squared is the same as A minus B dot A minus B. Correct? Okay. We also saw a property that said we could do the distribution to it too, right? This word right here. So we can do that distribution. So let's do that. So I have A squared minus 2A dot B plus B squared. Okay? All right. So if I have that on this side, that, 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 and that can all cancel out, correct? So I'm left with negative 2A dot B equals negative 2A B cosine theta. So if I clean this up a little bit, get the cosine, the dot product in this case by itself, because that's the way they want it first. So the dot product is equal to the magnitude of A times the magnitude of B times cosine of theta. We also have the corollary to that, where we have cosine of theta equals the dot product of A and B over the magnitude of A and B. So we now have a way that if we have our dot product, we can find the angle. Or if we have information about the vectors, we can find what the dot product is in either direction. Taking the dot product and finding the angle is a lot more useful. But we have both ways. This is one of those proofs I typically do just because it's actually a straightforward, simple way to go through and do it, and most people can follow it instead of some of the other ones which are very complex. And I think if I had just told you this and said, here's what this is, I know somebody would have said, huh? Why? And I would have totally agreed with that because it just doesn't make sense on why that would exist. But using the law of cosines, we can actually prove out and come up with why that does exist. And then there's the corollary. All right, so let's use it. So if I have two vectors that have a length of 4 and 6, and the angle between them is pi over 3, we're looking for the dot product. So remember, the dot product is cosine theta. So this is just the magnitude of length. So I got 4 times 6 times cosine of pi over 3. So cosine of pi over 3 is 1/2. So the dot product is 12. All right. The more useful one, like I said, is finding the angles. So let's find the angles between these two. So if we want to find the angles between these two vectors, what's the first thing I'm going to have to find? So we've got my cosine of theta is the dot product of A and B over the magnitude of A times the magnitude of B. So I've got to find the dot product and the two magnitudes. So find me my dot product and my two magnitudes. So there is the magnitudes. Remember, it's just squaring each of the terms and adding them up, taking the square root of it. So the magnitude of A is 3. And the magnitude of B is the square root of 38. And then the dot product, remember, just multiply them. So 2 times 5, 2 times -3, -1 times 2. And we get 2. So then we plug that all in. So we get cosine of theta is 2 over 3 square root of 38. Now, how do I find theta? What am I going to use? Huh? It's not called the inverse cosine. No, that's actually why it's not called the inverse cosine. It's the arc cosine. Because the inverse cosine is secant, and secant's not going to get, that's just the reciprocal of it. So it's the arc cosine. Or cosine -1, depending on how you see it. Right? And then we just put in the 2 over the 3 squared root of 38. So we use Desmos. Now, depending on how you want your answer, depending on how it's going to be used, in most situations, actually having it set as the degree is actually going to be more useful for this stuff. So the final answer is approximately 83.8 degrees. So if you want it in radians, just put it in radians. So either way would have given you the fine answer. Most times when you're looking at angles between things, degrees is typically how we look at it. When you're looking at a function over time on a graph, that's where your radius or your radians come into play. Any questions on that? All right. What are some use cases for this? What are some things that we might want to find if I just give you 2 random vectors? What are some important things that we might want to look for? What are nice angles that are important to be used in situations? 90 degrees. So, right, we want to know if they're perpendicular. Okay, if we're looking at 2 vectors, we want to know if they're perpendicular to each other. That might be helpful, especially if we're looking at using it to find areas and things like that. We need perpendicular lines to be able to do base and height stuff. So determining if 2 vectors are perpendicular, kind of important. So how would we tell if they were perpendicular? What should happen in this process if they're perpendicular? So this would have to equal 90, right? Which would mean theta would be what? I mean, oh, sorry, let me rephrase this. What would cosine of 90 be? What's cosine of 90 degrees? 0. So that means this over here has to be 0, correct? So if cosine of theta is 0, this has to be 0. So does the bottom matter? The bottom can't be 0, right? The bottom doesn't matter. The only thing that matters is that top piece. So if 2 vectors are going to be perpendicular, I don't need to go through and do all that work. All I need to look at is my dot product. If my dot product, if A dot B equals 0, They're perpendicular. Okay? Because cosine of 90 is 0. So to determine if two things are perpendicular, I don't need to go through and do all the work to determine that, oh, yep, it comes out to be 90 degrees at the end. I just need to do the dot product. If the dot product is greater than 0, what kind of angle am I going to get? So let's go back to this. If the top is greater than 0, that means the top's positive, right? Yes? Okay. Is the bottom ever going to be negative? No, the bottom has to be positive, right? Because it's a length. So that means that cosine of theta is going to be positive, correct? So what kind of angles is that going to give me if cosine is positive? It's going to be acute because that's all the numbers from 0 to 90 degrees. So if my dot product is greater than 0, I'm going to have an acute angle. So yes, acute angles are less than 90 degrees. But that's what this means, that I'm going to have angles that are less than 90 degrees. If it's less than 0, which means my dot product's going to be negative, correct? Which values are going to give me negative values or negative cosines? Cosine of theta is going to give me a negative value. Is the numbers between 0 and, well, technically between 0 and 270, but what we're mostly concerned about would be from 90 to 180 or obtuse angles. For your cosine does this. So that's 90 degrees, 180, 270, 360. So here is your positive. So that's that. And then here is your negative values, which will give you those. So we might not be able to figure out the exact value. Well, we can by doing some extra work. But just by doing the dot product, we can get some information about that angle, which could be very helpful depending on which situations we're dealing with. The most important one, though, is if the dot product is 0, they're perpendicular. All right, so are those two vectors that I gave you perpendicular? Well, let's quickly find it. So we do 2 times 5 plus 2 times -4 plus -1 times 2. So 10 minus 8 minus 2 is 0. So yes, they are perpendicular. Okay. Now remember that a vector is just from the origin to a point. So in essence, by doing this, we can take any 2 points in the 3-dimensional plane and find the angle between. Okay? That's what we can use this stuff for. So It basically allows us to take 2 points. Well, if you're using the origin. So technically, yes, 3 points. Because these vectors are always going back to the origin. So you can do it from 3 points too. You just have to do a little more calculations on it. All right. Now, the next thing. So when we're looking at a flat two-dimensional plane, you really only have that one angle. Okay. However, when we're looking at a three-dimensional plane, or sorry, a three-dimensional space, when we're going from looking at one vector, we have actually 3 different angles. We have the angle from the x or the I vector. We have the angle from the y, which is the k, and then we have the or ij. J is y, and then k is the z. So we have 3 different angles that would allow us to go from our axes to that vector. Does that concept make sense? That we have 3 different angles. If we look at the picture a little closer. I forget I can't just zoom with my finger on that one. So you can see the 3 angles here. So we've got that one to the x-axis. We have that's the y. And then we have, or sorry, that's the z. That's the y. That was the z. They used y for z. A nice one. So that's the y. Yeah. So we have 3 different angles that we can get. Using the same concept that we just did, we can find those directional angles. And we actually are able to find the directional vector, the angle vector from it. So all right. If, let's go back to our wonderful equations here. If I'm looking at from the vector to my initial vectors, the I, the j, and the k, those are always going to be a length of what? 1. So that magnitude of b is just 1, right? So I don't have to worry about the magnitude of b. And the dot product is going to be multiplying it by 1. It's 1, 0, 0. So I don't even have to worry about that part. So when I'm doing it, we have the pieces. So the only parts that matter is the correct place. So if we're looking at the I, we're just looking at the first term in the vector. If we're looking at the j, we're looking at the second term of the vector. If we're looking at the k, we're looking at the third term in the vector. And it's just divided by the magnitude of whatever the vector is. We can then write that as a vector. And those are it's your cosine vector. So basically it's the angles, the angle vector. So let's find our direction angles for this vector. I'm just going to use X, Y, and Z because I don't feel like trying to make the funky Greek letters. So we're using our first ones. So first thing I actually have to find before I can even do these is I need to find my magnitude of A. So I got 1 squared plus 2 squared plus 3 squared. And 4, 9, 13. Wait, not 13, 14. All right, so my cosine of my x is 1 over the square root of 14. Cosine to the y is 2 over the square root of 14. And z is 3 over the square root of 14. So if we look at these, go back to our Desmos, and we're going to do the arc cosine of each of those. 1 over the square root of 14. And then 2 and 3. So we get 74.49 or 70.5, 57.7, and 36.7 degrees. So those are my directional angles. Yeah, so that'd be those would be the directional angles for these. So yeah, you could just it's each one individually. You don't have to write it as a vector or anything else like that. Yes, because in all honesty, when these are used, it's typically in navigation. So degrees make sense. All right. Any questions with that?
It's not like less useful about them, so you don't have to come back to you.
Well, because this isn't actually using, we're trying to tell you which directions you have to go based on where you're going from. So if we're going due north, which direction do I need to go to get to this vector? Basically, that's all you're using it for. You're not necessarily using it in terms of telling me where the vector is. You're telling me the angles it is from the origin, basically.
The position of the vector doesn't matter.
Right. So it's less useful in terms of telling you the position of where it is on the graph, like where you're going to, but it depends on what you're using that for. So, all right, let's look at a use case of this. Work. So, the formula for work, I'll actually write a little bigger. Is the magnitude of force times the magnitude of the distance times the cosine of the angle. And you can manipulate that in any direction to find out the pieces that you'd like from that. All right, so a wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal. Find the work done by the force. Here's your pretty wagon. Because you always have to have a picture. So we have our, remember the work is the magnitude of the force times the magnitude of the displacement times the cosine of the angle. So in this case, my force was 70. My displacement was 100. And my angle was 35 degrees. Multiplying that all together, you get 5,734 Newton meters or joules. What's this? We saw that already.
It's equal to a dot product.
Yeah, that's just the dot product, right? So your work could also be given by the dot product of your force vector times your displacement vector. So even if we don't necessarily know the angle, if we know the vectors, we still can find out the amount of work done. So this one doesn't have a pretty picture. We've got our force vectors given by 3i plus 4j plus 5k. And moves a particle from the point of 210 to 0.462. Find the work done. So we have our force vector. Great. We don't have the angle, so I can't use that formula. I need my displacement vector. They gave where the particle started and where the particle ended. So how do I find my vector from that? How do I find a vector from 2 points? Just subtract the 2 points because we're looking at how far it moved. So my vector is going to be 2 minus 4, 1 minus 6, and 0 minus 2. Now, it matters. Remember, when you're doing these, it matters the direction. So we started at P and we're going to Q. So P's got to be first. So my displacement vector is -2, -5, -2.
So you have to be subtracting like the other one.
Oh, did you? Wait. You're right. I did it backwards. As I'm saying, don't do it backwards. I'm doing it backwards. Okay, that's better. All right. So we now have our displacement vector. So if I want to find my work, I just need the dot product of these two. So it's going to be 3 times 2 plus 4 times 5 plus 5 times 2. So 36. Since the problem didn't tell us what units they were in, we actually can't do a unit. If we assume that it's in newtons and meters, we can then say 36 joules. And that's typically what displacement's typically given to you in meters and force is typically given to you in newtons. So. All right, let's give you guys one. Let's do this one. Do that one. Huh? Yes. Because going back to what I said previously, that joules is normally the newtons and meters. You could have left it in kilometers and just said it would be 1,000, but it would have been Newton kilometers. So we've got 1,500 times 1,000 times cosine of 30 degrees. That's it. So you get 1.3 million, basically. Yes, I totally rounded that answer because it's not exactly that. It's 1,299,038.106, approximately 1.3 million. We'll do torque when we do the cross product. So, yeah, you need the cross product to be able to actually calculate a torque. I think with those you can figure out horsepower from remember it. Yeah, there's that. All right. Yeah, I don't remember the power formula for horsepower. Hold on. Find me the triangle's the right triangle. While I figure out how to do horsepower because I don't honestly remember. Oh, horsepower is just work divided by time. So it's literally that divided by how long you took it over. You also can use torque to do it based on the RPMs and stuff too. How would you start this? Well, that's the first thing, right? Yes, we're gonna have to. If we do the dot product, comes up to 0. I know it's 9 degrees, so that would be the right angle. But what do I got to do first? I don't have vectors here. I got to find my vectors first. So right now I have 3 points. So we have P, Q, and R. So I've got those 2 vectors. So I've got vector PQ and vector PR that I would have to do the dot product of. And then I have that one. So I have vector RP and vector RQ. Because does a right angle, do all of them have to be right angles? No, only one of them has to be a right angle, right? Only one of them can be a right angle. Right. Exactly. So only one of them can be a right angle. And if you're just going to do one vector, you might not find the one that was right. So there's three angles that we have to look at. We also can look at that one. So we have QP times QR. So you have three different dot products that we have to do. Now, the nice thing is for example, those two, all it is the signs are changed. So when you find one, you can just reverse the signs to find the other one. So that'll save you a little bit of time. And once you find one that's zero, you're done. So if you get lucky with your first shot. Let's see. 2 minus 1 is 1. There's 3. And negative 2. Five. I already did that one, didn't I? Which one did I miss? Oh, RQ. I'm like, wait, I'm getting the numbers and I'm like, these numbers sound familiar. So 2 minus 6 is negative 4. 0 plus 2 is 2. Negative 4 plus 5 is 1. So we got 4, negative 2, negative 1. Okay. So now I got all my vectors. Now we can do our dot product. So PQ times PR. So I've got 5 plus 3 minus 6, which does not equal 0. And I don't even care what the number is. I just know it doesn't equal 0. RP times RQ. So I got 20. Negative 2, negative 6, which also does not equal 0. Negative 4 plus 6 minus 2, which does equal 0. So yes, it's right angled. So if you have a triangle, you have to find. Notice, I'm not even looking for the angles. I just want to know if the question was, is it right angled? So I'm looking for one of the angles to come out, one of the dot products to come out to be 0. Because that means they're perpendicular, which means it's a right angle triangle. I'm done. Like that's all for dot products. And there's no time for me to start cross products tonight. So
Yeah.
What you did made it a lot more simple.
my biggest problem with physics is like there's so many formulas and stuff like that that it's like if I sat down and did it, I probably could figure it out, but I never actually had to. I was lucky. My college allowed my computer science classes to count for science ones. So I did programming instead of physics and biology and chemistry and all those other classes.
I think to me it sounds the best part of some sort like the forming, but I just need to understand it.
Yeah.
I mean, that sounds like the funnest physics when I hear about it.
Physics it's the application of math. So it's like it's like a chicken and egg, which came first, the application or the actual math. So I'm as a mathematician, I'm going to go with the application came first. Somebody saw a problem and they wanted to figure out how to do it, and then they created the math to figure it out.
So kind of how eventually the egg came to be.
Yes, like which came first, the chicken or the egg? Well, the chicken evolved.
Yeah.
Yeah, exactly. So, all right. All right. I'm good. Have a wonderful night. I'll see you on Thursday.
Yep.